Hi, and welcome back to my channel. If you're new here, my name's Harry, and I'm an engineer trying to land my first role in data science. In today's video, we're going to be learning how to create an interactive visualization dashboard in Python. An interactive dashboard is a great way to visualize insights from your dataset and the results of your data analysis. For this project, I'm going to be using a dataset from gov.uk that lists all of the sale history for property within England and Wales between 1995 up to today. This is a large dataset with over 28 million rows, so it should make for an interesting project. I've also been keen to explore geospatial plots. For anyone that's not familiar, these are map-based plots that are great for visualizing data when it's by location, so this project will be perfectly suited for that. For this project, I'm going to be using Plotly Dash. So what is Plotly Dash? Dash is an open source Python framework created by Plotly that allows you to create interactive web applications. Dash is written on top of Flask, Plotly.js, and React.js. I've played around creating several plots with Plotly, which is its own Python package. You can create plots within your scripts or notebooks just like you can with similar packages, such as Matplotlib and Seaborn. I really like how easy plots are to generate and the fact that they're interactive. Plotly Dash allows us to make a nice looking and functional dashboard with these plots. There'll be three main sections to this video. First of all, we'll be looking at processing our data ready to use with our dashboard. Second, we'll look at creating first a single page dashboard, and then we'll convert this into a multi-page dashboard. Finally, we'll look at deploying this to the web so that you can access it from anywhere to share it with your friends and colleagues. Feel free to skip ahead to the parts that are of interest if you don't want to follow the project end to end. So let's get into it. Before we can start, we need to import the packages that we'll need for the project. To start off with, I'm just going to import the packages that we need for the data processing. I'm going to be using pandas for processing my data, so we'll do a pip install on pandas first in my command prompt. Because I'm working with such a large dataset, I decided to use DAS to speed up the processing when importing the dataset. DAS data frame helps process large tabular data by parallelizing pandas, so I'll do a pip install of Dask. If you're working with smaller datasets, this might not be necessary. I also plan on doing some geospatial plots as mentioned in my dashboard, so I'll need GeoPandas to help do this. Now we've got our packages installed, let's go ahead and create a new notebook in our project directory. We'll first import the packages we just installed, so that'll be pandas as PD, DAS data frame as DD, and GeoPandas as GPD. So let's now import or read in the data using Dask. I'll start by specifying the path to the dataset, which in my case is the pp complete CSV, as you can see in the raw data folder. I'll then define the column names I want to use, which I've already got written down here. I'll then define each of the column data types as a string, other than price, which I want to set as an integer. I'll also set my transfer date column to be passed as a date. There's one column I won't be using in my analysis, and that's the transaction ID column, so I'll define a list of the columns I want to keep and exclude this from it. We'll then read in the CSV using dd.readCSV with the arguments that we've just defined. Finally, we'll run compute on the DAS data frame to generate the pandas data frame. After just over a minute, we now have our data frame. But before proceeding, we need to do some cleaning on the data. As all of our analysis is going to be done by location, primarily by the postcode, we need to drop any rows with no value for postcode, which you can see is true for around 46,000 rows. We'll start by dropping these rows without any postcode. Within the property type column, we can see it can take several values. We have D for detached properties, S for semi-detached, T for terraced, and F for flats. Finally, we have O for others. I want to drop all property sales with the property type of other. This is a large mixture of property types, largely the sale of large pieces of high value land that we're not interested in for this analysis. So we'll drop those rows. We'll then just tidy this up by sorting the data frame by the transfer date. So let's take a quick look at our data frame now. On the left you can see we've got the price paid and the transfer date, several bits of the address information for each property, and some other details like the property type and its new build status. If we do .info on the data frame, we can see that after cleaning we're still left with over 28 million rows of data. At this point, I needed to work out how to segment the data for analysis. Plotting the whole dataset felt impractical due to its size. I decided I wanted to be able to visualize the data by region. So within England and Wales, we have 10 regions, some examples being the South East, Greater London, and the East Midlands. So I'll need to add a new column called region that we'll need to infer from the postcode. As we'll see later, the GeoJSON data that we'll be using breaks regions up by the postcode sectors within it. The postcode region can be inferred from the postcode column values by taking the first string of characters, the space, and the first character of the second string. So I'll need to create a new column called postcode sector. So I'll start this by creating a new postcode sector column by applying a lambda function to the existing postcode column that finds and grabs everything up to and including the first character after the space. And once that's complete, we can take a quick look and check that our postcode sector looks okay, which we can see on the far right hand side here. We'll then need to create a new region column by first reading in a CSV that I have that defines postcode regions by their prefix. We'll create a new dictionary that captures the postcode prefix and the region from the CSV. First, we'll create a temporary postcode prefix column in the main df where we extract the postcode prefix from the existing postcode. We'll then map the region to each postcode in our main df using this dictionary. Finally, we'll exclude all data from properties within the Scotland region, as we've got very little data for this region. We'll also drop our temporary prefix column. The last modification that we'll make to the data is just to split the transfer date into separate month and year columns to make our lives easier later. So that's the pre-processing done, so we'll next look at the files that we'll need to create for the geospatial plots. First, a quick terminology session for working with geospatial plots. We're going to be working with shapefiles. This is a data file format used to represent items on a map. From the shapefiles, we're going to generate GeoJSON files. GeoJSON is a JSON format for geodata. It's GeoJSON files that we'll need to pass to Plotly to represent the different areas of the map. We'll be working with choropleth plots. These are plots that use different hues to colour polygons as a way to represent data levels. Okay, so let's get started with this. I found a website called Open Door Logistics that provided shapefiles that represented the UK postcode boundaries. Each boundary represents a postcode sector. GeoPandas makes converting the shapefile into GeoJSON super simple. So I'll add the files that we've downloaded from Open Door Logistics to our project directory. GeoPandas makes converting the shapefile into GeoJSON super simple. We just read in the shapefile, then use the toFile method to export this as a GeoJSON file. After running this, we've now got our GeoJSON file that includes all the postcode sector boundaries. Taking a quick look at this, you can see we have the postcode sector defined in the name key, followed by a bunch of coordinates to define the boundary edges. We now want to create separate GeoJSON files for each of our regions so that we can plot on a per region basis. This will also allow us to limit the amount of GeoJSON that we're passing when creating each plot. We can read in our postcode area CSV again, then read in our GeoJSON file that we just created using GeoPandas. Next, we'll create an empty dictionary where we'll store all of the geodata for each region. We can grab the postcode sector from the GeoJSON using the name key. Then we can merge the geodata with the postcode regions data frame to give us a data frame that includes the geodata with the region column. We'll then iterate over each region within the merged data frame and populate our dictionary. So we now have a nested dictionary with a key for each region. Within each of these, we have each postcode sector with the geometry data. Finally, we just need to export the GeoJSON file for each region from our dictionary. After running this, we can see the files that we've created and the GeoJSON within them. Okay, we now have our GeoJSON. Now we just need to process the data we want to plot. I'm going to first calculate the average price for each postcode sector by year. I want to end up with a CSV for each year within the dataset that includes the columns region, postcode sector, year, average price, and the volume of sales. So we can take a quick look at the data frame that we've got as a result from this. Now that's been created, I'll loop through each year within the data frame and export the data for the respective year to a new CSV. After running this, we can go ahead and see the files that we've now created. Next, I want to zoom out a bit and do the same as before, with average price by year, but this time for the region instead of by postcode sector. As we'll end up with less data, I'll be exporting this to just a single file for all regions for all years. So just checking the head on that new DF, we can take a quick look at the results. After running that, we can take a quick look at the output file. I next want to inspect the year-on-year price delta by postcode sector. For this, we can use PCT change within pandas. As the first year will have no previous year to compare with, I'll make sure to set all of the first year deltas to 0. We can take a quick look at this DF and inspect some of the deltas. This looks good, so we'll proceed with exporting this to a CSV for each year. We'll first drop any rows with a null delta. As before, we'll then create a CSV for each year, which includes the deltas by postcode. Finally, I want to inspect the volume of sales by postcode sector by year again. So I'll do the same as before, just this time doing a sum on the number of sales within each sector for each year. Again, exporting for each year to its own CSV. And we're now done with the data processing, so let's move on to creating the dashboard. I've got a pretty good idea of how I want the dashboard to look. I want to have multiple pages with a navigation bar at the top of the page. Below this, I want 2 drop-downs, one to select the region of interest and the other to select the year. On each page, I want 2 plots, each filling 50% of the width. As a first step, let's install the packages that we need for building the dashboard. Let's do a pip install on Dash for creating the dashboard app. This package can take a few minutes to install. This should also install Plotly, which we'll be using for creating the plots, but you can run pip install Plotly just to make sure. Before jumping into the code, there's a couple of important features to Dash to understand. Dash applications are made from 2 fundamental building blocks. The first is layouts, and the second is callbacks. Layouts simply describe the look and feel of the apps. Dash HTML components allow us to create and style basic HTML content like headings, body text, and images. Dash core components allow us to create interactive elements like the plots, drop-downs, sliders, and so on. Callbacks are used to make the dashboard interactive. We can create functions which are triggered on events, such as changing selection on a drop-down. We'll start by creating a simple page with 2 plots. Let's create a new Python file called home.py. I'll import HTML, input, output, and callback from Dash. We'll also need GeoPandas, Pandas, and Plotly Express. For now, I'll create a simple dictionary with a couple of values from our dataset to populate the drop-downs we'll create. We'll then create a Dash app with the Dash class. Next, we'll create a basic layout using app.layout. We'll create a new div using html.div, and within this, a drop-down first for the region. We can do this using dcc.dropdown. We'll pass arguments, the first being ID. I'll use region dropdown for this. We then need to pass a list of dropdown values. For this, we can use list comprehension on the dictionary we created earlier. The last argument we'll pass is value. This is the default value that will be selected. Now I just need to do the exact same thing again for the year. The last part of the layout that we need to add for now is the plots themselves. I'll create a new div and then use dcc.graph with the ID argument. For now, we'll just use plot1 and plot2 as the IDs. At this point, we can try running our Dash app. We can use the following if statement to run it. If we then run the script, we'll get a URL for the app, which we can open with Control and left click. So here we are. We've obviously got some work to do yet, but we can see we have our drop-downs for the year and for the region. We can also see that we've got a few values coming from that dictionary. You can see we've got 2 plots below, but you can see that they're currently empty as we haven't defined what to plot here. So let's go back to our script and press Ctrl+C in the terminal to stop the Dash app. The first thing we need to do to populate our plots is to add our callbacks. These callbacks will be the trigger for our plots to be updated when we change the value selected in the dropdowns. We need to define the callbacks with @app.callback. We first add our outputs. These are the calls for our function to update the plots. So within a list, we'll use the output class passing the ID of the first plot, which we defined as plot1, as the first argument. Next, we'll pass the component property, which in this case is a figure. Then we just need to do the same again for plot 2. We can now define our inputs. In our case, this is the 2 dropdowns. So within another list, we'll use the input class and pass the ID for the first dropdown. For us, this was the region dropdown. For the component property, we'll pass a value of value. Then the same again for the year dropdown. Now we need to define the functions that create the plot figures. Let's create a new function called updateFigures that takes the argument selected year and selected region. With this function, I want to create a choropleth map to plot the average price by postcode sector for the selected region and year. We'll load in the CSV that includes the average price data for the selected year into a data frame. We can next filter the data frame to only include rows for the region that we've selected in the dropdown. Now we need to load the GeoJSON file for the region that's been selected. We can define a path, then use GeoPandas to read this in. Then it's just a case of defining the figure. We can use Plotly Express to create our choropleth map box. We'll pass in our data with the first argument, then our GeoJSON. For locations, we'll want to use postcode sector as a column from our main data frame. We'll next need to pass the feature ID key to tell the function where within our GeoJSON to match the postcode sectors on. For my GeoJSON, this is in properties.name. I'll then define color, which is what will be used to define the hue of each region by the average price column of our data frame. For the mapbox style, we'll use Carto Positron. We can now return the figure and we're ready to test this out. We just need to make a temporary modification to the callbacks to only expect one figure, as we've only written one function for one figure so far. So let's start the app by running the script and take a look. We can see the first problem is the position that the map is defaulting to and the zoom level. If I zoom out and move over a bit, we can eventually find our plot, so we'll need to make sure we update that. We can see we've got each of the postcode sectors for our selected region, which is the southeast. If I hover over the different sectors, we can see the sector names and the average price for that sector. It doesn't look very pretty at the moment, but we can look at styling the app later. So let's jump back to our code and make some changes to improve this. The first thing I want to do is make sure our plot is roughly centered on the region that's been selected. So I need to provide position and zoom levels for each region. To keep the code organized, I'm going to create a new Python file called config.py to store this information. I'm actually going to store the values for the dropdowns in here too, so that we can use a single dictionary to store the dropdown values and the center positions and zoom levels for each region. So I'll first delete the dropdown values dictionary from the app.py file. Then in my config file, I'm going to use this dictionary which I've already created. Within this, you can see I've got a nested dictionary. The first dictionary defines each of the regions, and the lat and long positions for each of the centers. I've also got zoom levels for each of the regions too. Then I've also added the year values, which is just a list created from a range of our first and last years from the dataset. I can now move back to the app file and import the app_config dictionary from the config file. Now I just need to update the options argument in the dropdowns to use the app_config dictionary instead of the dropdown values one. Then, going back to our plot function, I'll fetch the configurations for the selected region. We can then use the center and zoom values with the center and zoom arguments. I also want to set the opacity to 0.5 to improve the look a little bit. I'll also add a title quickly and update the label text. I'd also like to show the volume of sales when you hover over each sector. We can do this easily by adding volume is true to the hover data argument. If we run the app now, we can see that this is looking much better. You can see we're roughly centered on the selected region and the hues look much nicer. We've also got our title and label, and when we hover over a sector, we can see the sales volume. We can now see that the dropdowns are fully populated, and changing the selected value updates the figures as we'd expect. One thing we can notice with some regions is that the hues can heavily be skewed by particularly expensive sectors, so it might be nice to scale our legend by percentiles. An easy way to do this is to go back to our code and import NumPy. If you haven't already done a pip install on NumPy, go ahead and do that now. We can then define key min and max values using np.percentile. I'll use the 5th and 95th percentiles for now. We can then add these to our figure function in the range_color argument as a list. If we then go back to the app, we can see the hues are looking much better scaled for our dataset. So at this point, it might be worth trying to improve the organisation of our code as we start to prepare for creating multiple pages. I'd like to put all of my plot functions in a separate file, which I can then call from each of the pages. So I'll create a new Python file called helpers.py, and I'll start by copying my function from home.py, deleting it and then pasting it into helpers. Let's now move our import from app into helpers. In my case, that's pandas, geopandas, plotly express, numpy, and our app_config. We can now import our plot function from helpers into app. First, I'll update the names to be less generic, so I'll call it average_price_map_fig. Then in app, we can import this function from helpers. Finally, we need to define a new function to call our function from helpers. We need to define this to pass our input arguments. So I'll call this new function updatePlots with the selected region and year as arguments. Then I'll return our function from helpers. So let's check our app still works okay after making those changes. And loading it up, it looks good and is working as it was before. Okay, so now I'm going to go ahead and create a new function in helpers for the second plot. For this plot, I want to create a bar plot to show the average price and number of sales by year for all the years we've got data for. So I'll do that and I'll join you afterwards. Okay, so you can now see the code I've got here for my bar plot. I'll go back to home.py and import the new function from helpers. I'll delete the temporary callback and uncomment the original so we can now call back both of the figures. I'm then going to update my callback function to call both figures and store them as fig1 and fig2. I can now return these, and once that's done, we can start the app again and check that it's working correctly. Great, we can now see that we've got both plots. They're both showing and they both look good. At this point, we can start thinking about our multi-page functionality. Before doing this, we'll of course need to create another page. I'm not going to show you this process as it's exactly the same as that we used for home.py. I'll create a new Python file. Within that, I'll create a dash app. I'll then define the layout, create the callbacks, and create the functions and helpers. Finally, I'll then add those functions to the callbacks. So here's my second page. In this page, I've created another two figures, this time plotting the year-on-year average price delta that we calculated during our data processing. The page looks very similar to home.py that we created earlier, just with different functions being called and different figures as a result. It's a good idea to assign different IDs to the graph objects when you define them in the layout and then again in the callbacks. You can see here that I've defined the new plots as plot 3 and plot 4. We now need to create our app structure, and for that we have to create a new file called app.py. This needs to be in the root directory of our project. We'll then have to create a folder called pages, and within this directory we'll store each of the Python files that represents a separate page. In our case, this is my delta.py and home.py. So let's start with app.py. We'll first import dash, DCC, and HTML from dash. We then create an app using the dash class, using __name _ as the name, and set the usePages argument to true. We can then define our app.layout in the same way as we did before. We'll use the code snippet from the dash documentation for now to show basic page navigation and the page container. It's page container that represents the relevant page that we're trying to load. We can also add headers and footers to our page in the layout here, but we'll come on to that later. We can then finish off by running the app in the same way as we've done before. We now just need to make a couple of modifications to our existing pages to allow them to work with app.py. So let's start with home.py. We need to delete the creation of the dash app and replace it with register page. So let's first import register page from Dash. We'll use name for the name, and we can then define the path to the page. As this is my home page, I'll just use a /. We then need to update the layout to just use layout, and no longer use app.layout. Next, as we've defined the app in app.py, we need to modify the callback statement. First, we need to add callback to the imports from Dash. Then we simply remove app.dot from the callback definition. Finally, we can remove the if statement to run the app from within the page. We can then do the same for my second page. For this page, I'll use /delta as the path and price change as the name. Again, I'll import callback from Dash and update the callback definition. If I now go back to the app script and run it, we can see our dashboard. You can now see that we've got some very basic navigation and can click between our pages with a simple header at the top. Again, at this stage, it's not very pretty, but we can address that now. I'd like to use a dark theme for my dashboard, and when looking at the best ways to do this, I came across a library called Dash Bootstrap Components. This is built on the Bootstrap Components library and allows us to use Bootstrap component libraries as native Dash components, which makes implementing it on our dashboard very easy. There's several themes to choose from, which you can see examples of on the Bootstrap Components website. Personally, I like the Slate theme for this project, so I'll be using that for the dashboard. First, we need to do a pip install of Dash Bootstrap Components. After doing that, we can import the package into each of our pages, starting with app.py. We start by adding a stylesheet link within the Dash class. We can use the external stylesheets argument and pass the Slate theme within that. I want to use a simple navbar from the package, so I'll start by defining that. We can use the navbar symbol class, and within the children, assign nav items for each of the pages. We can define the display name here, and the href should match the path that we provided in register page. I'm also assigning a heading to the navbar in brand. For this one, I'll use property investment dashboard. I'll set the href of the heading to the home page and set the color to dark. I'll also add a simple footer to the page with dbc container with a link to my GitHub. We can then update the layout to include our new navbar, the page container again, and the footer within a div. We can check the navbar out by running our app, and we can see that it's already starting to look much better. I want to update the layout so the two plots on each page show side by side. To do this, we'll need to import Dash Bootstrap components to each of our pages. Let's start with home.py. We'll then delete our existing layout so that we can use the Dash Bootstrap components instead of the core Dash ones. Within the layout, we'll first create a dbc container. I then want to add two rows, one for the dropdown and one for the figures. So in the first row, I'll add a column for the region dropdown label and set its width to 1. I'll also add a class name to the containing div so that we can add additional styles to these later. Then I'll add a column for the region dropdown with the same code to get the values from our config file. I'll set the width of this to 2. I'll then repeat these steps for the year label and the year dropdown. I'm also adding class names to the rows so that I can reference this later for additional styling. And then finally, I'll create a row for the figures and add 2 columns for each of the figures. And I'll set the width of both columns to 6. I'll also set the height of the figures here within the style parameter. Launching the app, we can now see the result for the home page. It's looking much better, and I'm now starting to feel quite happy with this. We now just need to do the same process for the second page, but I'm not going to show that as it is the exact same process. The last big thing that I want to do now is to update the styling of the figures to match our dashboard styles. To do this, let's go into our helpers file. We can use the update layout method to change some of the properties of our figure. I'll start by adding a paper BG colour and the plot BG colour of the choropleth figure to match our theme. I'll then also update the font colour to white. I'll then repeat this process for the bar plot, this time adding some titles to the axis and updating the position of the legend. Running the app again, we can see that we're getting pretty close. So I'll just do the same process for the other figure functions. Again, I'm not going to show that as it's exactly the same process. There's just a couple more tweaks I'd like to make to the styling. For this, I'll use an external style sheet with some custom styles. So in the root of the project, I'll need to create a folder called Assets. In this, I'll create a new CSS file called Custom CSS. I can now reference the class names we assigned earlier in the layouts. I'll paste my code that I wrote earlier for this. These are just updating the colour, the margins, and fonts of some of the elements. To reference these styles, we just need to add the style sheet name in the external style sheets parameter of our app.py file. I can show the result by checking the dashboard again. You'll notice that I've moved some of the elements in the navbar to suit my preferences, and a couple of other small changes. The last thing I'd like to do on my dashboard is to add another page, but this time using a slider element. I'd like to plot the fastest growing sectors and fastest declining sectors by the year-on-year average price change. The user should be able to select the slider to show the top number of results they want. For example, they could select the top 10 fastest growing sectors or the top 100. I'll start by duplicating my homepage so that I can reuse some of the code. I'll first update the page name and path. I'll then add a new row to my layout and add a label and the dash slider element. I'll first assign an ID, then the minimum value the slider can take, the maximum value, and the step size. Then I just need to assign the default value with the value parameter, and finally, the tooltip location. As my slider is going to be horizontal, I'll have the tooltip show at the bottom. I now need to update my callbacks to include the slider as an input. I just need to add the slider ID and the component property. Next, it's just a case of creating the functions to plot the figures. I'll fast forward through that and join you afterwards again. Now that's done, I can quickly show you what the function looks like, and just point out the fact that I have an additional argument compared to the other figure functions. This allows me to pass the value from the slider. I just use this value to pull the head or the tail of the data frame with the number of required rows. Once I've done that, I can update the functions themselves, making sure to pass the slider value in addition to the region and year arguments. Great, now I just need to add my new page to the navbar in app.py, and then we're ready to check out the dashboard. So as you can see, we've now got all three of our pages showing in the navbar. At this point, I feel pretty happy with how the dashboard looks, and we're ready to move on to the next step of deploying it. After some searching, I came across Python Anywhere. They offer servers with Python environments pre-installed. This will allow us to get up and running a lot faster. Python Anywhere offers a free plan that will be fine for this project, but I'm going to use the Hacker subscription at $5 a month, as this allows you to use a custom domain. So we'll go ahead and sign up for an account, and once that's complete, we'll have access to our Python Anywhere dashboard. We'll start by opening Bash and install the packages that aren't included in Python Anywhere by default. So first, we'll do a pip install on GeoPandas, and then once that's done, the same again for Dash Bootstrap components. I've found sometimes that the Dash package pre-installed with Python Anywhere isn't the latest, so we'll also run a pip install on Dash upgrade to make sure it's up to date. For this tutorial, I want to use a custom domain, so you'll need to go ahead and purchase one. For this video, I'll be using a domain that I've purchased through GoDaddy. The domain I'll use on the final version is actually different. It's thepropertydashboard.com, which I'll link below, so you can check it out for yourself. Now we have our domain, we'll go back to the Python Anywhere dashboard and click the Web tab. We'll add a new web app and specify our domain. It's important to add the www dot before the domain here. We can click Next, and then select Flask as a framework, as this is the framework that Dash is built on. I'll then select the latest version of Python. We'll leave the Flask app path to the default value and click Next. We've now created our web app, so the next step is to copy the CNAME value provided in our dashboard so we can point our domain to it. So I'll copy this value, and then I'll go to the DNS settings in my domain manager. I'll start by deleting any existing CNAME records. I'll then add a new record, selecting CNAME as the type, www as the name, and then the value, which we've just copied from Python Anywhere. We'll now have to wait for the DNS changes to propagate across the web, so in the meantime, let's get our files for our application onto our Python Anywhere server. The easiest way to do this, in my experience, is using GitHub. I won't talk through the details of this as there's plenty of other videos on the topic. It's worth mentioning though that we should add a git ignore file to the project to make sure that we're not pushing the large raw data CSV to Git. Once that's done, I'll push the changes to Git, and you can now see the files in the repo that I've created for the project. Going back to Python Anywhere, let's navigate to the source code directory. We can see the default Flask file in here, so we'll go ahead and delete that. I'll then go ahead and start a bash console in the directory, then clone the project repo that we've just pushed to GitHub. Once that's complete, we can see that we now have our project files in a new directory. Let's copy the directory name and go back to our web app. I'll then update the source code directory and the working directory to match the directory we just copied. Now we just need to make a small change to our configuration file, so we'll click on that and replace the final line to import our -app from the app file, then set the application using app.server. We also need to update the project home to the same directory we just set for the source and working directories. Once we've done that, we can save the changes. Now we want to reload our application, and once that's done, we can test it out. So long as your DNS changes have propagated, you should be able to see your dashboard. If you can't, wait a couple of hours and try again. So we can see our dashboard, and it looks just like it did when we were working in a local environment. One thing to notice is that the site is currently showing as not secure, as we have no SSL certificate. Python Anywhere makes it really easy to fix that. We just need to go back to our dashboard in a moment. We can check out our dashboard quickly and make sure that it's all working. Mine looks good and seems to work exactly as it did when locally. So now back to our Python Anywhere dashboard. We can scroll down to security and enable the Let's Encrypt certificate, then click Save. We can then set Force HTTPS to Enabled to make sure that visitors are redirected to the secure URL. Now we just need to reload the app and refresh the page, and we can see the site is now showing as secure. So that's it, we're done. We've successfully created our dashboard. I am going to go back through the code and make a few changes to improve performance. That being said, I'll upload the final version of the code to my GitHub, which will be linked below. If you want to check out the final version of my dashboard, you can do that by heading over to thepropertydashboard.co.uk, which I'll also link below. So thanks to anyone who made it to the end of the video. Don't forget to like and subscribe for more tutorials like this, and I look forward to seeing you in the next one.